Hi, good morning. I'm Xilin. I'm from University of Birmingham. So today I will talk about the STORMS project, about buried infrastructure. So our project also includes colleagues from UK Centre for Ecology and Hydrology and also British Geological Survey. So why buried infrastructure? It's really complex, but it's essential because it provides water and energy and communication services to our cities. So that's why we are looking into it. However, there are a lot of damages to buried infrastructure every year, and it is very costly. Over 2.4 billion per year, and for those damages, a lot of them are actually associated with weather and climate. There are mainly two types. One of them is from flooding and river and coastal erosion, and the other one is from differential ground movement. Actually, both of the impacts are listed in the third round of adaptation reporting power and also CCI3 as well, climate risk assessment report. However, there's no national scale risk assessment tool existing for that purpose. And consequently, there's no quantitative climate impact projections for pipelines as it's stated by CCI3. So now our aim is to develop a comprehensive weather-related risk assessment framework to understand the potential impacts and also to estimate how the risks may change under climate change conditions, and also co-develop resilience measures with the stakeholders so that it can be used for adaptation purposes. So the progress so far, I think we have defined the impact for weather and climate scenarios and confirmed them by sensitivity analysis. The other progress we have made includes developing a comprehensive risk assessment framework for this. And we have also engaged with stakeholders, for example, Cadent, for example, Line Search Before You Dive, and also the water companies. So this gives you an overview of what has been done in this project. So now I will give you a bit more details. This graph gives you an overview of the climate risk assessment model that we have developed. Basically, we have categorized the risk into two types. The first one is from surface water, and the other one from ground movement. For surface water risk, it's mainly flood-driven erosion, and the other one about ground movement, it can include loss of load bearing and also differential subsidence and expansion. And to support this risk analysis, we have used different types of data, including rainfall scenarios and soil properties, and also soil moisture scenarios. And finally, we combine those two types of risks and then visualize that for stakeholders or end users to use them. So this gives you an overview of what the risk assessment framework is about. So one of the data sets we have used is the UKCP 18 soil moisture data. It's a probabilistic climate projection based on RCP 8.5. It was created by UKCEH using the grid-to-grid hydrological model. And for this data set, we have ensemble monthly mean soil moisture for each month from 1980 to 2080. And we're also working on an enhanced version of that using some outputs from the HydroJuice program, which is a NERC-funded program, using some newest results such as the British groundwater model. Another data set we used is the soil parent material. It's a British Geological Survey product. It's 1 square kilometer resolution. Basically, it contains essential information that could be used for estimating the ground movement and also the surface erosion as well. Within this project, we're also developing a method to access this data set from the UK Soil Observatory using a web API. For example, if you look at a region, you can link directly to that so that you can get more detailed information for that region. So that's one of the work that we're currently developing within this project as well. So to estimate damages for pipes, we have created a two-dimensional finite element model which conceptualizes the pipelines into a line. So in this way, we can simulate the soil pipe interactions. And also, we can use all the data sets we have just mentioned to estimate the soil stiffness and expansion shrinkage volume, which is validated by three-dimensional finite element model and also experiments as shown in this picture as well. Once we have got the data and the model, we can calculate the risk. So with the finite element model, we can calculate the displacement of the pipes. We compare that with the maximum displacement for pipe failure. We compare those, calculate the ratio, and then decide the risk into 3 different categories. It has been categorized into low risk, medium risk, and high risk. And apart from using a more complicated finite elements model-based approach, we also developed a simple matrix-based approach, which combines all the information we have got into one single matrix and do the calculation. Later, I'll also show the difference. So we have also got the risk calculation from surface water. And we use the rainfall scenarios based on UKCP 18, and our colleagues in CEH are doing some frequency analysis to try to see how it might be changing in the future. And we use that as rainfall scenarios to fit that into a hydrodynamic model called SyncFlow. And we are using that to calculate the soil erosion. It's a very expensive model to run, but we were able to run it across the northeastern England. So that example was shown for the 2016 storm Desmond event. We can calculate which place has the high potential of soil erosion, and we can overlap this layer with the pipelines, then identify the hotspot. So that's how we calculate the risk from surface water. It's a bit similar to surface water flood risk assessment, but we have extended the model's capability to calculate flood-driven erosion as well. So this is the progress that we have made. Part of the workflow is already on DAFNI. This just gives you a screenshot of what are the input parameters and the data slots are. And once we have got outputs, we will be able to visualize the risk for certain pipelines. This is just a case study that we have done for the national gas transmission pipeline. So basically, what you have got is an overview of the risk for national gas pipeline across the Great Britain. And then we can also zoom in into individual pipe segments to see what are the actual risk factors and risk ranking for this. So that's how it might work. So in terms of the results, both of the methods, the finite element method and the simple matrix-based method, give consistent results, including picking up the high-risk area. And in those reports, it was said that areas around the south of England and around London have higher risk. So actually, our model are able to pick that up. But we do see benefits of using a more sophisticated model using finite element method, because it actually considers the properties of individual pipelines, such as the diameters, the material, and potentially we can bake the asset condition into that as well. So we can have much granular results, and therefore to give a bit more details. Now, model is also able to give an estimate of what might happen in the future. Basically, this is a comparison between May 2020 and May 2080. We should be aware that we shouldn't really take the results as like for like. It's more estimate rather than what will exactly happen in that month, that year. But we do see that in some highlighted area, we can see an increased risk. So that's the other way that the model might be useful. And so now, I guess now work can be quite useful for helping to adapt to climate change and increase resilience. And there are several tangible outcomes. One thing is that we can understand network-wide and national-scale climate risk much more comprehensively. And this can be useful to inform national guidance, such as CCRA4, which is currently being developed. And the companies and end users can also use that work to test different scenarios to see what might change. For example, if they change the pipeline material, what would be the consequences? If the soil moisture change, what would be the consequences? So that's the benefit of being a process-based rather than entirely data-driven model. And we do have some challenges during the project. For example, the validation of the model is very challenging, and there is a lot of uncertainty. One reason is because that it's difficult to get data to properly validate, for example, the leakage of the pipelines. I guess this is also linked to other wider challenges, such as cross-organizational data sharing that has been highlighted in this morning's keynote speeches. And then in the next step, we will continue to validate the model and also complete the risk assessment. we will run the model through all the climate scenarios that has been generated to complete that risk assessment. And also, we will talk to other stakeholders, for example, the utility companies, to try to get them on board and run training sessions for them to get access to this, maybe use their own data as well. So this would be something that we'll do next. And we're also exploring linkages to other data portals such as NUA and Jasmine. We're currently working with DAFNI on that. Hopefully, it can further extend the applicability of the model. For example, make it a digital twin that can feed real data into that, real-time data into that. So that's all my talk. Thank you.